In exercise 9.2, you're trying to do a synthesis question. Now, in synthesis questions, they give you a reactant, they give you a product, and you have to figure out how you can make that transformation happen. And this is really our goal for this class. We're trying to turn you into something in between a chef and a magician, where you can take something that's toxic and turn it into a medicine, you can take something that's inexpensive and turn it into something that's expensive. And the first step for these is really to have the reactions memorized. So from this point on in this homework set for chapter 9, the assumption is going to be that you already have the reactions memorized. There's no way really to do these problems without already knowing those reactions. And hopefully once you have those memorized, you can use these videos to help you see how to think through what the information they give you and associate it with the recipes that you know by heart. So let's start with this one. You see an alkene, you see a pi bond, and that should make you think of addition reactions. So you're sort of narrowing it down in your head. We know you have to do addition now, as opposed to substitution or elimination. Well, what do you add? They don't have any recipe here, that's what we have to come up with. So instead we're going to look at the things that are on the product that are not on the reactant. The first thing that stands out to me is this bromine. You have a bromine there, and that bromine is not there in the original molecule. There is something else, and it's a little harder to see. If you ever can't find a second thing that was added, draw in the hydrogens on the 2 carbons in the double bond, both in the reactant and in the product. Now this carbon at the bottom has 4 bonds drawn, so it doesn't have any hydrogens on it. At the top, there are only 2 bonds drawn to that carbon. That means it must have 2 hydrogens. The same carbon in the product has only 1 bond drawn. That means it must have 3 hydrogens. And so now that you have those drawn in, you could see that one of those hydrogens was not there in the reactant. And so you've added a hydrogen. Now to make this look a little less cluttered, I'm going to erase those hydrogens that didn't react. So we added an H and a Br. That gives us some information about what type of recipe we'd have to use. If you add a hydrogen and a halogen, that's hydrohalogenation. So you would want to add H, in this case HBr. Now it's not done there, because if you remember in hydrohalogenation, you had 2 options. You could either just add the HBr, in which case you get Markovnikov addition. The H goes to the less substituted carbon. Or you could add the HBr in the presence of a peroxide. Peroxides are molecules that have 2 oxygens bonded to each other. And in that case, you would still get the addition of the H and the Br, but it would be anti-Markovnikov. The hydrogen would go to the more substituted carbon. So let's look at our product and see where the hydrogen went. The hydrogen is attached to a carbon that's just bonded to one other carbon, so that's primary. The other atom in the double bond was bonded to 1, 2, 3 carbons in the product, so that's tertiary. So the carbon that the hydrogen added to the less substituted carbon. In other words, it was Markovnikov addition. Hydrogen goes to the less substituted carbon. And so the recipe that you'd want here is just HBr. That's the only thing you need to add there. Okay, let's try the same thing with this next product. So we notice we have the same reactant. You'd look at this is the same thing that we have up here, and you notice you have a pi bond there. And so instantly you're trying to narrow down, step by step, what type of reaction you need to do. When you see a pi bond, you think, okay, I have to do an addition reaction, as opposed to a substitution or an elimination reaction. Both of those require a leaving group, and we don't have that on this reactant. Instead, we have extramolecular glue, a pi bond that we can use to stick things onto this molecule. So now we're looking for things to add. Well, what do you see in the product that's not there in the reactant? You have a bromine. Bromine is definitely not there in a reactant. And I don't really see a second thing. So if you can't find the second thing, because you always add 2, if you can't find the second thing, draw in the hydrogens on the 2 carbons in the double bond. So this starting molecule had 2 hydrogens there on the carbon at the top. Still has 2 hydrogens, so that didn't change. The other carbon had 0 hydrogens in the reactants and has 1 hydrogen in the product. So that hydrogen appears. It wasn't there in the reactant. And the other hydrogens that were there, I'm going to erase. Those didn't change. So we added an H and a Br. Well, that's hydrohalogenation, so we know we're going to have to add at least hydrogen and the halogen HBr. But we have the same question as last time. Do we have to add a peroxide? Do we want Markovnikov addition without the peroxide or anti-Markovnikov addition with the peroxide? So for that, we have to look at what type of carbon the hydrogen went on. Here the hydrogen is on a carbon that's bonded to 1, 2, 3 other carbons. So that is tertiary. The other carbon that was in the double bond, that carbon is just bonded to one other carbon, so that is primary. So the hydrogen went on the more substituted carbon. That is anti-Markovnikov addition. And so we would not get the correct product if we just used HBr. That would give us Markovnikov addition. That would give us the product above. Here, we have to include in the recipe, or else it's completely wrong, we have to include the peroxide. So this peroxide is the answer. Well, the HBr in the presence of a peroxide is the answer for this synthesis. If you throw that into your bubbling cauldron, in your witch's brew, then you'll end up making this transformation happen, this anti-Markovnikov addition of a hydrogen into halogen. So this is sort of dipping our toe into this pool of synthesis problems. So far, these transformations are just one step. We'll gradually work up our way to 4 or 5 in organic chemistry, 2 all the way up to 10 steps in order to transform a reactant into a product. But here we're taking baby steps. We're just trying to find one recipe to make one transformation happen.